Hyperplanes in two-dimensional Euclidean space cannot separate data points arranged in concentric circles or complex interlaced patterns. This topological constraint necessitates a transformation that alters the relative distances between these points to find a separable structure. A feature map function lifts the input data into a higher dimensional space, where linear separation becomes mathematically possible. In 3 dimensions, a flat plane can easily divide points that were previously inseparable when confined to a 2-dimensional plane. Explicitly calculating coordinates in high-dimensional spaces is computationally expensive and memory-intensive due to the combinatorial explosion of terms. This problem is known as the curse of dimensionality and limits the practical use of direct feature mapping in large datasets.
The kernel trick provides a solution by allowing us to work in the high-dimensional feature space without ever visiting it. We compute inner products directly in the input space using a specialized kernel function instead of explicit feature vectors. A kernel function takes 2 vectors from the input space and returns a scalar value that is identical to their inner product in the feature space. This mathematical identity allows us to perform geometric operations without knowing the exact mapping function. The symmetry and positive semi-definiteness of a function are the requirements for it to be a valid Mercer kernel. These properties ensure that the kernel corresponds to a valid dot product in some reproducing kernel Hilbert space.
Positive semi-definiteness requires that for any finite set of points, the associated Gram matrix has non-negative eigenvalues. This condition prevents the existence of vectors with negative squared lengths in the feature space, preserving the Hilbert space structure. In functional analysis, a kernel induces a linear integral operator on the space of square integrable functions. This operator maps a function to another function by integrating it against the kernel over the entire input domain. Mercer's theorem provides a spectral decomposition of the kernel into an infinite series of eigenvalues and orthonormal eigenfunctions. This series converges absolutely and uniformly over the compact domain of the input space. The feature map can be viewed as an infinite dimensional vector, where each component is an eigenfunction scaled by the square root of its corresponding eigenvalue. This perspective clarifies how a finite kernel can represent an infinite dimensional space. A Hilbert space of functions is called a reproducing kernel Hilbert space if every evaluation functional is continuous. This means that 2 functions that are close in the norm of the space must have values that are close everywhere. Continuity of the evaluation functional ensures that the mapping from a function to its value at a specific point is a bounded linear operator. This is a restrictive property not shared by all Hilbert spaces, such as the standard space of square integrable functions. The Riesz representation theorem states that for every continuous linear functional, there exists a unique element in the Hilbert space that represents it. In the context of evaluation, this element is exactly the kernel function centered at that point. The reproducing property identifies the function value at any point x as the inner product of the function with the kernel at x. This fundamental identity links the algebraic structure of the Hilbert space with the pointwise values of its functions. Because the kernel acts as the representer of evaluation, the inner product of 2 kernel functions at different points, x and y, is exactly the kernel evaluated at those 2 points. This consistency is why the function is called a reproducing kernel. Learning algorithms often seek to minimize a functional that combines a loss term on training data with a regularization term. The regularization term is typically the squared norm of the function in the reproducing kernel Hilbert space. The representer theorem proves that the function minimizing the regularized risk must be a linear combination of the kernel functions evaluated at the training points. This reduces an infinite dimensional search to a finite dimensional optimization over coefficients. Any function in the Hilbert space can be decomposed into a component in the span of the training point kernels and an orthogonal component. The loss term only depends on the values at training points, which are unaffected by the orthogonal component. The regularization term increases with the norm of the function. Adding an orthogonal component only increases the total norm without improving the fit on the training data. Therefore,
the optimal function must have a zero orthogonal component. Substituting the representation into the objective function transforms it into a problem involving the Gram matrix and the vector of coefficients. We solve for the optimal weights by applying standard linear algebra or quadratic programming techniques. The Gaussian radial basis function kernel is defined by the exponential of the negative squared Euclidean distance between points. It is one of the most widely used kernels because it corresponds to a feature space of infinite dimensions. Functions in a Gaussian reproducing kernel Hilbert space are infinitely differentiable and smooth. The choice of kernel bandwidth determines the length scale over which the function can vary, allowing for control over model complexity. Polynomial kernels represent a feature space consisting of all possible monomials of a specific degree. For a degree 2 kernel with two-dimensional input, the feature space includes squared terms and interaction terms like x multiplied by y. Support vector machines use the kernel trick to find the hyperplane that maximizes the margin between classes in the high-dimensional feature space. The decision boundary in the input space appears nonlinear, even though it is a flat plane in feature space. The coefficients alpha are non-zero only for the support vectors, which are the points closest to the decision boundary. This sparsity makes the model efficient, as the decision function only depends on a small subset of the training data. Kernel principal component analysis performs dimensionality reduction by finding the eigenvectors of the Gram matrix in the feature space. This allows for the extraction of nonlinear features that capture the underlying manifold structure of the data. To perform principal component analysis, the data must be centered in the feature space. While we cannot center the mapped points directly, we can center the Gram matrix algebraically using a specific transformation involving a matrix of ones. Gaussian processes extend the kernel trick to a Bayesian framework, where the kernel defines the covariance between random variables. The kernel specifies our prior beliefs about the smoothness and periodicity of the unknown function being modeled. The covariance matrix for a set of input points is exactly the Gram matrix produced by the kernel. Prediction at new points is done by conditioning the joint Gaussian distribution on the observed values using the Schur complement. A kernel is stationary if it only depends on the vector difference between 2 points, making it invariant to translations in the input space. If it only depends on the Euclidean distance, it is isotropic and invariant to rotations. Bochner's theorem states that every continuous stationary positive definite kernel is the Fourier transform of a finite positive measure. This creates a powerful link between the spatial properties of the kernel and its frequency spectrum. Random Fourier features approximate kernels by sampling from the frequency distribution guaranteed by Bochner's theorem. This allows us to map data into a low-dimensional space where a simple linear inner product approximates the original kernel. Standard kernel methods scale cubically with the number of data points, making them difficult to use for millions of observations. Approximation techniques like the Nystrom method use a subset of the data to estimate the full Gram matrix. The Nystrom method approximates the integral operator's eigenfunctions by using the relationships between a small set of landmark points and the rest of the dataset. This results in a low-rank factorization of the kernel matrix. Many kernels are associated with Sobolev spaces, which are Hilbert spaces of functions with a certain number of square integrable derivatives. The kernel choice implicitly defines the differential operators used to measure function smoothness. The Matern kernel family generalizes the Gaussian kernel by introducing a parameter that controls the differentiability of the resulting functions. This allows for the modeling of processes that are less smooth than those produced by the Gaussian kernel. Changing the regularization parameter lambda traces a path of solutions from a perfect fit on the training data to a completely smooth function. Optimal generalization is usually found at an intermediate point that balances error and complexity. The kernel trick is not limited to linear regression and can be applied to logistic regression and other generalized linear models. By replacing the linear predictor with a function from the Hilbert space, we obtain a nonlinear classifier with probabilistic outputs. Kernels can be defined on non-vector data, such as strings, graphs, or trees, by designing functions that measure the similarity of these structures.
String kernels compare the number of shared substrings to enable machine learning on genetic sequences or text. Graph kernels compare the connectivity and node attributes of two graphs, typically by performing random walks or comparing local subgraphs. This allows for the classification of chemical molecules, where the graph represents the atomic bonds. Multiple kernel learning seeks to automatically learn the best combination of several base kernels for a specific task. The resulting kernel is a weighted sum of the base kernels, where the weights are learned during the training process. The performance of kernel methods is highly sensitive to the choice of parameters, like the Gaussian bandwidth. Cross-validation is typically used to search the parameter space and find the values that minimize the validation error. Choosing the right kernel is a form of prior selection and remains one of the primary challenges in using kernel methods. Without domain knowledge or extensive validation, the performance of a kernel machine can be suboptimal. The neural tangent kernel describes the behavior of infinite-width neural networks during gradient descent. In this limit, the training of a network is equivalent to a kernel regression with a fixed kernel defined by the architecture. As the network width tends to infinity, the change in the neural network function during training is governed by the neural tangent kernel. This theoretical breakthrough links deep learning to the classical theory of reproducing kernel Hilbert spaces. The main difference between standard kernel methods and deep learning is that kernels use fixed feature maps, while neural networks learn features. However, the kernel perspective provides tools to analyze the convergence and generalization of deep models. Generalization bounds in reproducing kernel Hilbert spaces are often based on the Rademacher complexity of the function class. These bounds depend on the norm of the solution and the properties of the kernel, rather than the number of parameters. Kernel methods are stable algorithms because a small change in the training data leads to only a small change in the resulting function. This stability is a direct consequence of the continuity of the evaluation functional in the Hilbert space. A kernel is universal if its associated Hilbert space is dense in the space of continuous functions. Universal kernels, like the Gaussian kernel, can approximate any continuous function to arbitrary precision given enough training data. The kernel trick remains a pillar of machine learning by providing a rigorous mathematical framework for nonlinear analysis. By bridging the gap between finite data and infinite dimensional spaces, functional analysis ensures the robustness and efficiency of modern predictive models.